Alright, so okay, so this one then is not. So if they're both 1, this is fine.
Right.
But if one of them is 0, it's no longer fine. Alright, so this one needs to be fixed. Let's look at this one. If they're both 1, this gives us no information on z. If one of them is 0, it forces z to be 0. So this condition forces z to be 0 if one of them is 0. And then if both of them are 1, no information. So now we just need a condition that works when both of them are 1. Okay, so let's try to fix the other condition we had. So we need something where if they're both 1, it's going to be okay. So we could try maybe x plus y minus 1 less than or equal to z. Let's try something like that. If they're both 1, then the left-hand side is 1, and that forces z to be 1. If even one of them is 0, then it's trivially true and it's no information. And so it has to be something of a slightly different form than this, because, as was pointed out, otherwise we're going to get z equals, and z is not going to be a sum like this. So now, if both are 1, you get 1 is less than or equal to z, therefore z equals 1. If at least 1 is 0, then no information.
Because we're saying that z is binary too.
Z is binary. And so this will allow us to create a new binary variable that's the product of two binary variables. So what this means is you actually can multiply binary variables. Normally that would not be a linear relationship. Squaring, cubing, raising things to the 4th power, usually that's not linear. Here, it's still not linear, but it can be linearized at the cost of more variables and more constraints. Do you think this is expensive or not expensive?
Well, it depends relative to what.
So every time I have a product, I have to add in one new variable and 2 more constraints. So if you have a lot of products, this will very quickly become expensive. It will increase the complexity greatly, but it can be done. So one of my favorite quotes is about the singing horse. How many of you have ever heard of a singing horse? So what's amazing is not that the horse sings well, but that the horse sings at all. And that's the way you should use something like this. It can be done, okay? You can make this linear. If there's time, I will talk about horses of different colors. And I'll prove that every horse has the same color. Any questions about this? So do you agree that we can now represent products of binary variables as a new binary variable? What's really nice about this is you can write any number in a binary expansion. So you can actually convert this to being a result for general integer programming problems. It becomes a computational nightmare to use, but theoretically, you can convert all of this. If you find a fast way to do binary integer programming, you can do an enormous amount. Okay, so what I want to do now is I want to play the game of what's linear. It's, not going to be, sold in stores, but, it is a fun game to play in stuff like this. Take relationships that are not linear and try to make them linear. So let's come up with a list of things you would like to linearize. So we've already heard max. Min. There's something else that said, Lucky said this earlier. Or. Well, if we're going to put up or.
Exclusive or.
Exclusive or. Have I told you my philosophy story with or? When I was an undergraduate, I didn't get credit for a Spanish class. It was a long story.
Yeah, you told me.
Did I tell you guys?
No.
So I very quickly had to add a philosophy class to fulfill distribution requirements my spring freshman year. And the philosophy professor gave us, this was logic theory, a exam where 50% of the exam was 10 questions, and this instruction said, state which of the following are true or false. It's things like, P and Q implies not P or not Q, stuff like that. But technically she didn't use the exclusive OR. She technically, they were all truth value determinable. And so the answer to the 50% of the exam was yes, all sentences are true or false. I was not brave enough to do that on the exam. She told me afterwards she would have flunked me. But I don't think she could have. I think that one I could have won. But XOR means at most one, and in fact exactly one of them is true. So, if the Yankees are playing the Red Sox, either the Yankees or the Red Sox will win. Why?
Rules of baseball.
Rules of baseball. Baseball games cannot end in a tie.
Is that All-Star?
No, all baseball games.
No, All-Star
Was
games
it-
have never been tied.
Not anymore.
Oh, okay.
The great Bud Selig
Really?
has decreed that baseball games will not end in a tie. It's one of the worst things that could happen in humanity.
What's the longest baseball game ever?
There's been 30-inning games.
Jesus.
I think there's been a minor league game around 40 innings.
I thought it was 26.
Maybe it was 26.
Recent history, 22.
I mean, I know there was an 18. I think there was an 18 last year.
A couple years ago, the Indians played the Yankees about 20 or something.
Right. And then the Houston Astros had a great one in the playoffs a couple of years ago, where the teams were down to just one last pitcher. But no, I mean, it would take us too long to go into exactly how bad it would be for humanity for a baseball game to end in a tie. But it's just catastrophic. Okay. So baseball games can't end in a tie. So you can use the exclusive OR there. What else might we want? And, if we're going to have all this stuff, we should have and.
And
What's an and?
wait, isn't that one? Maybe I'm wrong.
I'll put in one more. 3-letter abbreviation starts with A.
Average.
Not average, because average just adds stuff into. Average is linear. That we can do easily. Absolute value. So the idea is you want to be able to handle stuff like this in the confines of linear programming. So you can introduce new variables, you can introduce new constraints, and you want to be able to handle stuff like this. We saw it was really nice to have a constraint like this or this or this. And there may be sometimes ways around it where you don't have to use or. Maybe there's better things. Like, let me take these products and then sum them, and then that sum has to be able to, maybe there's better ways. But let's try to figure out how to do OR. So again, we'll do max first. I don't know what the best order is to do them. Let's do x and y are in 0, 1. Let's do the maximum of x and y. So how would you do maximum of x or y? So this one's not too bad. So what's the maximum value going to be? I'm sorry?
1.
Or? Or 0. So it's going to be 0 or 1. So how would we figure out if it's 1 or 0? So what does it mean to be the maximum of x or y? I'm sorry?
It's the bigger one.
Okay. I was thinking a little bit more than what Cam would tell me. What does it mean if z is the maximum of x and y? Unwind it for me.
At least one of them is 1 and this one.
This isn't really long, okay? Go back to what Cam would tell me. If z is the maximum of x and y, then...
Y can take my value greater than Z.
So how do you tell if z is the maximum of x and y? I have a candidate. I think...
greater than or equal to everything.
Okay, so give me some constraints.
Z is greater than or equal to x.
And?
Y.
Two constraints.
Yeah.
Z is greater than or equal to x, z is greater than or equal to y. Since z is binary, are we
And
done?
X and Y.
I'm sorry?
You have to assume X and Y are 2.
Yeah, so we'll assume x and y are binary. So this gives me z is greater than x, z is greater than y. There is a problem, yes.
Z less than or equal to 1. Or no.
They're both 0. If they're even.
So if one of them is 1, we're fine. If both of them are 0, we're in trouble. What else do we need?
X is not equal to y.
We don't want to put a not equal.
Z less than or equal to x plus 1.
Good. So now if we do x plus y greater than or equal to z, so if at least one of them is 1, this constraint is vacuous and doesn't have anything to do. If both of them are 1, what does that do? So was this what you said, x plus y is greater than or equal to z? Alright, so let's see if this works. So if x is 1 or y is 1, we're fine here. If x is 1 and y is 1, this constraint has nothing to do. If one of them is 1 and one of them is 0, we're fine. The only difficulty is if they're both 0. If they're both 0, we don't want z to equal 1. But if they're both 0, this forces z to be 0. So this constraint only kicks in when x and y are both 0. So this would do it. Okay? So I like this idea of viewing these constraints as almost, they turn on at different times. When different conditions happen, different ones are in play. This condition is vacuous. It doesn't really have any bearing on the problem if x plus y is greater than or equal to 1. But when x and y are both 0, then it becomes very important. So this allows us to handle maximum. Okay? This is just doing maximum of 0, 1 binary variables. We could actually do more general, I give you 2 variables. What if I want to do a maximum of 2 variables? So you might want to get to that later. Right now, again, we've only done maximum of 0, 1s. But maybe I want to consider something more general. In binary integer programming, do you ever have to consider something more than just a 0, 1? Yes. You might have to add a bunch of 0, 1 variables. So this is not necessarily general enough for us. So if you want, let's try to look at a more general case right now. And so now, let's assume 0 less than or equal to x, y less than or equal to some big bound b, and maybe discrete multiples of delta. You know, I'm doing things integer. You know, if you want, think of x and y as, 0, 1, 2, 3, 4, 5, all the way up to b. So we might as well just adjust things so that delta is just 1. If you are looking at a company like Walmart and you want to look at its revenue, its sales, all of its numbers, it's discrete. It's effectively continuous because going from a couple of cents up to billions of dollars is so many orders of magnitude. It's as if it was continuous. But on a fundamental level, you can look at Walmart as discrete. So let's assume now x and y are discrete. They're integers between 0 and b, and I want z to be greater than, I want z to be the maximum. So I can start off exactly as before, z greater than or equal to x, z greater than or equal to y. So far so good, right? This forces z to be at least as large as the maximum, but now we want to make sure z is not larger than the maximum. So how would we prevent z from getting too large?
We would use we're about to discover our OR,
Okay.
and we have to show that z is equal to x or y.
Ah, I like that. Excellent. Z equals x or y. Beautiful. Done. So now we just need to figure out how to do things with OR. Okay. Now, of course, you might worry a little bit, well, maybe I can only do OR with binary integers. And x and y here are not necessarily binary integers. But I could probably do some kind of trick and pass on. Maybe I'll call it, oh God, it's been so long since I've written the script Z. I'll use zeta. Zeta. I'll do z sub b for binary. Maybe I want z sub b to be x sub binary or y sub binary, and do some kind of game like that. And then that should be enough to do it. And then if xb equals 1, or maybe if zb equals xb, then z equals x. If zb equals yb, then z equals y. Something like that. Now I need to do an if-then statement. So that might be something else I want to put on my list. If-then. But the idea is we want to use these logical connectives to build up more and more complicated expressions to put into the model. So if you're actually trying to write something down, you want to be able to do stuff like this. So now we have to figure out how to do OR. Okay, so let's figure out OR. So x and y are 0, 1. So we want z equals x or z equals y. So how would we do this? And then the other question is this how we actually want to phrase the OR statement? So if x and y are different, then z could be anything. If x and y are the same, it has to be the same. So any thoughts as to how you would attack something like this?
Obviously z equals x plus y over 2. If, depends on the if. They're the same. But if they're different.
So if they're both the same, everything's okay. If they're not both the same, this is 1/2.
Yeah. The floor on the computer.
And that's the thing is, how do you do this linearly? So if we looked at x plus y over 2, if they're both 1, it's going to be 1. If they're both 0, it's going to be 0. If they're mixed, it's going to be 1/2. So what if I took something like this?
Then you get problem when both are 0.
When they're both 0, then you get 0 is less than or equal to z, and so but it's still valid. If one of them is 0 and one of them is 1, then that forces z to be 1.
Yeah, that's fine.
Which is fine. If they're both 1, it forces z to be 1. So this would work, except for the case when they're both 0.
But you add in a special piece, add in another.
So how would I then deal, what constraint would I have to add if they're both 0?
X plus y is greater than.
Yes. So if I then did x plus y is greater than or equal to z, if they're both 0, that forces z to be 0. If they're not both 0, there's no information. So does this work?
Why do we want to force z to be 1 when we have x equals 1 and y equals 0?
I'm sorry?
Why do we want to force z to be 1 when x and y are different?
That's exactly the issue. This is not the same as x or y. This is, z is the larger of x or y. Right? What did we just find out? What did we just do here? If x is greater than y, this forces z to be the greater of the two. It's not a true OR. what did we actually just discover?
The max.
Max, right? So we just did max by mistake. Well, okay, this is good. Now we don't need to use OR to do max. But so, again, I am deliberately not prepared for today's lecture because I don't want to go through the material in the right order. I want to have conversations about how you look at these things, how you attack them. And so, what are natural conditions to write down and investigate? And so, unfortunately, when we investigate this, this is one of the biggest problems in programming, is you suddenly assume something. And you don't even realize you're assuming it. We've suddenly forced z to be the larger of x or y over here, and not the more general case. So again, if they're both 0, there's no problem. If they're both 1, there's no problem. But unfortunately, if they're opposite, there is an issue. So what else could we try? So if they're both 1, that forces z to be 1. If they're mixed, this is 1/2, and that's going to force z to be 1.
So the top constraint is no good.
So we need to modify it a little bit. It's not a horrible constraint.
Why don't you subtract a half?
Excellent! Subtract a half. Now let's see, if they're both 1, we get 1 minus a half, which is a half, that forces z to be 1. If they're both 0, oh good, negative 1/2 is less than equal to z. No problem. If they're mixed, we now get 0 less than equal to z. No information. So if they're mixed, either is fine for z. If they're mixed over here, either is fine for z. Z is then free to be x or y. So this is a really nice way to do OR. And the whole idea is we can actually subtract off this minus a half. So when you're looking at these things, in some sense, notice that everything is looking like, a x plus b y plus c greater than or equal to z. And I can switch the inequality by just multiplying a, b, and c by negative 1.
You still have to keep the second.
I still have to keep the second, yes, I need both of them. But this would be the true, this is no longer max, this is now OR. And so everything we're looking at is of this form. So if you want, you could just search inequalities like this and stop playing games with a, b, and c to try to figure out the functional form. So the idea is, how do you figure out what brought you to subtract the minus 1/2? What made you subtract a half?
Because of the problem we had with 1/2.
So we had a problem with 1/2, so maybe if I subtract 1/2 it looks better. And so we're trying to take this and we're trying to tweak the form. What's a good thing to put in here? Could we do something other than a half?
Minus 1/2 minus 1/100. Well, no, you don't need a half.
So I'll leave that as a question for you to think. Does it have to be minus a half here, or can you put in something else? That shouldn't be too hard to just play with and see. Does anything else work?
Doesn't it have to be any, it can be any constant, so that the left side of the inequality is less than 0. Because if it's greater, if that side is at any point greater than 0, then you don't have.
Well, if I put in minus 5/2, I'll have trouble.
Yeah, just needs to be less than 1.
So maybe it's anything between minus a half and minus 1.
Okay. Yeah, I see what you're saying.
So maybe any number maybe between minus a half and 1 and minus 1 works. Alright, so this gives us OR. XOR is, either z equals x or z equals y, but not both. Now that you would not really phrase exactly like this, because of course, if my x and y are 0, 1 condition, 0, 1 random variables, well, it's possible they could both take on the same value. So in terms of doing a lot of linear programming problems, we're not going to look just at binary variables. We're going to look at conditions. So you might want to have condition 1, maybe x is greater than or equal to a, and condition 2, y greater than or equal to, something like this. And you go through trying to figure out stuff like this. So I'm not going to go through the details of how you do all the stuff like this. It's in the notes I've provided you on my homepage. I don't believe this is in the book. I don't believe the book goes through how you linearize things. Alright, so we've got, or, how would you do and? So we can see actually this and is not going to really work as well for just binary variables. We would really want more conditions like this. I want this condition to hold and that condition to hold. And so
You just use those two constraints.
So we could just put those two constraints in directly. And say I want x to be greater than or equal to a, I want y to be greater than or equal to b. So, an and constraint doesn't seem to be that bad. Right? I want this to hold, and I want that to hold. Okay? Put them in the list. One of the hardest parts is sometimes the things that seem almost by definition. Now, I remember spending an hour my first semester in my math class before we realized the answer was just by definition. This is how we've defined the thing, therefore it's true. And is not difficult. What if we wanted or to hold for these two conditions? I want either x to be greater than or equal to a, or I want y to be greater than or equal to b. So how would we do? I can't put both of those conditions in now.
Is this exclusive or that you want?
Let's do inclusive or now of conditions. Let's talk about conditions. We just did for binary variables. Let's do conditions now. I want either this condition or this condition to hold. So how could I have something like that?
Wait, can you clarify what you're doing again? I didn't
Sure.
understand what.
I have some expression involving x, some expression involving y. I want x to be greater than or equal to a, or I want y to be greater than or equal to b. And think of x as some linear combination of random variables. So some linear combination of things. Maybe it's x1 plus x3 minus 4 x4 plus 8 x5. I'll just call that whole thing x. Some long expression. And I have a similar expression over here.
I mean, you can take the minimum of a and b and then just make x greater than or equal to that.
But these may not be the same subsets of variables. I have some combination of variables here, I'll call that x. I have some combination of variables, I'll call that y. I want either these combinations to be greater than x, so I want either the Yankees to be playing the Orioles or the Red Sox to be playing the Blue Jays. I want one of those things to happen. It's okay if both happen, but I want at least one to happen.
Just solve two linear programming problems.
I don't want to split this up into two linear programming problems to solve, because then every time I have an OR, I'm doubling the number of problems to solve. I want to somehow create constraints and feed those constraints into the model. So I need to somehow introduce indicative variables as to whether or not this condition is true. So what I could do is maybe I'll have ZA equals 1 if x is greater than or equal to a, and 0 if x is less than a. ZB equals 1 if y is greater than or equal to b, and 0 if y is less than b. So imagine I could do that. So now ZA equals 1 if this condition is satisfied. ZB equals 1 if this condition is satisfied. And now, how would I do OR? I need at least one of them to be satisfied. So at least one of x is greater than or equal to a, y greater than or equal to b is true. So imagine somehow I have a way to get these zb's and za's. We haven't figured that out yet, but let's say we could do that. So za will just tell me whether or not this condition is satisfied. zb will tell me if this condition is satisfied. How would I do OR?
Sounds good than equal to 1.
Excellent, the sum is greater than or equal to 1. za plus zb is greater than or equal to 1. That forces at least one of them to be satisfied. So if I have ways of detecting if a condition is true, it's then very trivial to put in something like OR. So this would be OR. Can somebody give me XOR?
Just make it equal.
Make it equal. So ZA plus ZB equals 1. Think of it as either the Red Sox play the Yankees or the Yankees play the Orioles. You're not going to have both of them happening. So now it all comes down to, can I write a detector condition that ZA equals 1 if x is greater than or equal to a and 0 otherwise? So does everyone agree we just have to figure out how to do this and we're done? Okay. So the inputs, we've got to have x, a, and ZA have to come into our relationship. So let's look at x minus a. So if x equals a, this is going to be 0. If x is greater than a, it'll be at least 1, 2, 3, 4, 5. And then we want to somehow compare this to ZA.
This one.
I'm sorry?
Let me think about that.
So it might help to say 0 less than or equal to x less than or equal to some big number m. We'll assume all of our quantities are bounded, so they can't get too large. So if I look at something like this, these are so if x is less than a, this will be a negative in the numerator.
We're assuming they're integers.
We'll assume they're integers. The world has been discretized. So again, Walmart, you can assume their revenue is discrete. So if I look at something like this, if x is greater than or equal to a, this is going to be a positive number. What if I try something like this? When this is positive, it's going to force ZA to be 1. If it's negative, we have no information. But this is at least a good way to start. Do I need this maximum here? Well, if this becomes really huge, I need to somehow scale things appropriately. And so it's nice to know these numbers are bounded. In any problem you look at, things are bounded. You cannot have infinitely large values in any of your programming problems. So it's not a big deal to assume there's some maximum value. So this expression is going to force ZA to be 1 if x is greater than or equal to a. Unfortunately, that's only half the problem. Now we need to force it to be 0 if x is less than a. Well, if x is less than a, this quantity is negative, it provides no information. So we need something now to handle the case when x is negative. So let me just move this over a little bit. So we have x minus a minus a half. Was it minus a half or plus a half? Plus a half.
Yeah.
It was plus a half, I think?
Yeah, it was plus.
Over m, and that was less than or equal to ZA. Alright, so now we need something that will force it to be 0 if x is less than a. So if we look at x minus a is now some negative number. And we've got ZA over here.
Since you're dividing, if you make the numerator negative,
Over
and then
here.
you're dividing by m, you're going to have a number between 0 and 1. So if you make it less than or equal to z, it's going to be less than 1, so it's going to be 0.
Are you talking about here?
Yeah. So like if you make it negative x plus a minus a half.
Okay, so you want a minus x plus a half?
I'm thinking about what the half sign. So now we want the case where a is bigger than x, right?
Right.
No, subtract a half.
Okay.
Or, I guess it doesn't really matter. If you just did a minus x over m,
Okay.
since m is bigger, that number will be less than 1, right?
So this will be less than 1.
So if you say less than or equal to z.
The problem
or
is,
greater-
if x is greater than a, this now fails. Right? So we need something that, this works fine if x is greater than a, and if x is less than a, it provides no information. We need something that provides information only when x is less than a. So a minus x would be a positive number. So let me see something like this. The problem again is if x is if x is greater than if x is less than a, this is a positive number. This forces z to be 0. But if x is greater than a, this is now negative, and so this would break down. So we need something slightly different than x minus a because we've already got that. Right? It can't reduce to something we've already seen. Right? We're close. Let's look at about 5 minutes left. So we've got 5 minutes to figure it out. So this gets us halfway there. If x is greater than a, forces z to be 1. If x is less than a, there's no information. So we need something that's going to turn on when x is less than a.
Just reverse a and x. So it'll be a minus x plus 1 half divided by m.
Okay.
Less than or equal to. Yeah, it's less than or equal to z.
Okay. So now, if x is less than a,
That's the exact same thing. Oh no, it's like.
it's not the exact same thing. So if x is less than or equal to a, this is now positive, and that forces ZA to be 1, which we don't want.
Oh. 1 minus?
I mean, we could do greater than or equal to. But then again, once x is greater than a, there's a problem. So maybe we could look at x minus a over m, maybe put the 1/2 outside things. Or maybe put like a 2m over here. If x is less than a, this is going to be negative, right? And so this will clearly be less than a half. And so if we said, we've got to be careful, this is not going to quite work, but that would force ZA to be 0. If x is greater than a, unfortunately now, this is not quite large enough.
Could you do a minus x plus 1/2 divided by m less than or equal to 1 minus a?
Okay, so we want to do x minus a plus a half over m, and you want to do 1 minus z?
Less than or equal to.
Okay, so now let's think.
Oh, a minus x.
A minus x. So if x is less than a, this is going to be a positive number, so that's going to force z of a to be 0. So if x is less than a, this forces ZA to be 0. If x is greater than a, this is negative. We've got to be careful now. If x equals a, this is positive 1/2. And that's going to then force z of a to be 0. So you might want to, maybe we drop the 1/2. If x is less than a, this is positive, so ZA has to be 0. If x is greater than or equal to a, this is going to be 0 or a positive number. We want to have no information in this case on z. And unfortunately, it looks like we're getting some information.
Maybe it would help if you tried to use some of the other operations we proved, like max and min.
I think if you just tweak this a little bit, you're there. We just have to put, I think, play games a little bit where we put the half. Maybe.
If x is greater than or equal to a, then the left-hand side is less than or equal to 0.
Okay, if x is greater than a, this is going to become negative, and then ZA is completely free. If x equals a, this is 0, and then we have no information. So maybe we need to subtract, if x equals a, so if we subtract a half, if x equals a, it's negative. If x is greater than a, it's negative. If x is less than a, it's positive. So I think this works. Okay, so this one will work. And that'll imply ZA is free. We got it with about 2 minutes to spare. Okay, but notice it's still of the same form, because we can bring this 1 over to the other side. We can bring the negative sign over. It's of the form, something times the first plus something times the second plus some constant is greater than or equal to the final thing. Everything is of these forms. It's how do you search through it. So we can get stuff like this very easily. So we've got, we did OR, it's OR, we did AND. Technically haven't done if then. Let's just do max. We did max, right? We did min. How about absolute value? Absolute value is really easy. I'm probably not supposed to say that as a professor, but it's really easy.
Wait, absolute value for binary?
No, for any expression. We want z to be the absolute value of x. Not necessarily binary. Just unwind, what does it mean?
The maximum x.
Z is the maximum of x and negative x. Right. Now that we have all of this stuff, it's very easy to get absolute value by using the previous stuff. So I think this is a good place to stop in terms of the formal lectures and whatnot. We've done, I think, a good amount of linear programming. You can read the notes, talk amongst yourselves.